Welcome back, guys. In today's video, I'm going to be covering the ideal gas law. So the ideal gas law is PV equals nRT. Now P stands for pressure, V stands for volume, N stands for the moles of gas, R is the R constant, which I'll come back to, and T is your temperature in Kelvin. So in order to use the ideal gas law, we actually need to be under a certain set of conditions, right? Because we see the word ideal come before gas law, right? Now, when is a gas going to behave ideally, right? We can only use the ideal gas law if we are under conditions that allow a gas to behave ideally. So under what conditions can we use the ideal gas law? So gases behave ideally, which I'll cover in a second, right? They behave ideally when the temperature is high and the pressure is low. So the higher your temperature and the lower your pressure, the more likely you're going to be able to have a gas behave ideally. Now, under low temperatures and high pressures, we are not going to be able to use the ideal gas law because that gas is going to start behaving in a non-ideal fashion. So let's say we meet the conditions and we can use the ideal gas law. What does it mean to say that a gas behaves ideally? So if we imagine this balloon or whatever it may be filled up with gas particles, right? And we are going to say that this is under high temps and low pressures, and we can say, yes, this gas is behaving ideally. We need to make two assumptions if we're going to say that a gas is behaving ideally, okay? So there's two assumptions we're going to make. One, that there are no IMFs for these gases, okay? So IMF stands for intermolecular forces, right? Intermolecular forces. And those are simply the interactions between the gas particles, right? So these interactions, right, we are going to assume that there are none taking place if a gas is behaving ideally. Now, what is the second assumption? So the second assumption is that the gas particles don't take up any volume. So what we're saying is, even though we can see these gas particles written out on the board here, we're actually going to assume that they don't take up any space in the container that they're in, right? So even though we can see them, we're going to say that the volume that they take up in that space is negligible, right? So we are not going to say that these gas particles take up any volume if they're behaving ideally. Now, let's say the temperature was low and the pressure was high, right? We cannot make these assumptions anymore. So if a gas is behaving in a non-ideal fashion, we have to take these into consideration, and we would have to take into consideration that volume that that gas takes up. So let's see if we can solve some practice problems, right, now that we know a little bit more about the ideal gas law and when we can use it, okay? So it says a 5-liter container is held at 25 degrees Celsius and 1 atmosphere of pressure. How many moles of gas are in the container? So if I see a problem like this, I definitely am thinking I'm going to use the ideal gas law. So I'm actually going to erase this and give ourselves some room to do some work here, okay? So if I write out PV equals nRT, okay, I have my pressure. Atmosphere is a very common unit for pressure, right? So I have 1 atmosphere of pressure. My volume, right, is 5 liters. It's a 5-liter container. Okay? We're trying to solve for how many moles of gas that we have. And then we get to our R constant, okay? Now there are many different values for the R constant depending on which pressure unit that you're in. However, the two most common pressure units that I see in problems are atmospheres and bar, okay? So it's going to change slightly depending on which pressure unit you're using. However, we're in atmosphere here, so I'm going to use 0.08206 liter times atmosphere over mole times Kelvin. Okay, now Kelvin is the unit for temperature that we need to be in, okay? So our temperature, right, is our last variable. Now, if we plug in 25 degrees Celsius, we're going to be wrong because this is Kelvin. So how do you convert Celsius to Kelvin? Well, if you have a value in Celsius, all you need to do is add 273 and that will get you to Kelvin. Okay, so if you add 273 to 25, you're going to get 298 Kelvin, which is the correct unit for temperature for the ideal gas law formula. Okay, now if you multiply this out, right, and you divide both things out from the other side, you should get roughly 0.20 equals N. So you would have 0.2 moles of that gas. Okay, so make sure you can pause this, go through this problem yourself, set that up, and divide out and get the right answer. Okay, so I'm going to erase this and move on to the next problem. Okay, so problem 2 says a 2-liter container has a pressure of 5 atmosphere. What would the new pressure be if we increased the volume to 1 liter? That should say decreased. If we decreased the volume to 1 liter. Okay, so we have this 2-liter container. Okay, and we're saying the pressure in here is 5 atmosphere. Okay, and now we have this other situation, right, where we now have this new volume at 1 liter, and we're trying to figure out the new pressure. So this is a classic example of a PV equals nRT problem or an ideal gas law problem. They're going to give you 2 scenarios and have you manipulate the variables around to see your missing answer or your missing variable. Okay, now there's a bunch of different names of people who came up with different variations of the formula. I don't like to remember that. I just like to set it up and cancel out what stays constant. Okay, so what I mean by that, if I write out PV equals nRT and PV equals nRT, let's see what stays constant both times. So I know first that the R constant is not going to change for either one of these. Okay, it didn't say that we're going to let out any gas or add any new gas to either of these containers, right, at the beginning or the end. Okay, so the amount of moles is not going to change of the gas, right? We're not going to let any out or put any in. Okay, now we are going to change the volume. Okay, so I don't want to cancel that out. And we are going to have a new pressure. However, the temperature is staying the same, right? It didn't give us any info about the temperature changing, right? Some problems will even go as far as say like everything else stays constant, but if you don't see that, you can assume that those things are staying constant, okay? So the only thing that we're changing is the pressure and the volume. So the way that you're supposed to set this up after you've done this is what we're going to say is that we can break this down into 2 separate scenarios with our 2 pressure values and 2 volume values, okay? And what we can do is we can say that P1, V1, okay, our first pressure and our first volume is equal to P2, V2, okay? So like I said, there's a bunch of different variations where if you cancel out different things, you can set something up just like this. So if you have a situation where they're changing things around, just write PV equals nRT for both situations, cancel out what stays the same, and set up an equality right where we can find our missing variables, okay? So let's plug in what we have. Our original volume is 2 liters, and our original original pressure, I should say, is 5 atmospheres. So it's 5 atmospheres times 2 liters, okay? Our second pressure is what we're trying to find, right? But our volume is now 1 liter, okay? So what we can do is 10 divided by 1 when we bring that to the other side, and our second pressure is going to be 10 atmosphere. Okay, so that's how you do a problem just like that. So make sure you understand what conditions we can use the ideal gas law under, the 2 assumptions with the ideal gas law. Make sure you can solve a problem and then do one of these tricky problems where you have to see what stays the same and what changes. Thanks for watching, and make sure to check out the channel for more videos.